Morning, everybody. Y'all doing okay? Doing well? Had a good break, I hope. Y'all want to see our pictures from our break? Do you care? Just take a couple of minutes. I know that you care, but let's see. We went camping one day, and we went to Mississippi, and it was my little girl's birthday. She turned 6, so we had like a few little friends over. Let's see. We made Easter eggs. It was Easter, yeah, it was Easter over break. Let's see. Oh, these are some of our Easter eggs. How about this one? You like this one? We took a clover and put it on the egg, and then we wrapped it up in like what's it that women put on their legs? What's it called? The pantyhose, yes. And wrapped it up, and then put it in the dye. We did with a clover, and my boy made this with a cross on it with tape. And let's see. Oh, this is my wife actually. Some of you know her. That was at Easter. And oh, this was camping. That's Lake Pontchartrain. We went to Fontainebleau State Park. We can't. It was cold, but the kids went swimming. They had this thing at our campsite. We don't know what it is. It's some kind of bug trap. But have you ever seen one of these? No, it was there. I don't know what it is. Um, let's see. This is me and my little girl, Ada. This is our family selfie out on the that pier out at Lake Pontchartrain. Y'all ever been out there to Fontainebleau State Park? It's a great park. Uh, see, this is my little girl's birthday. See my glasses? You got my glasses? They were hers, actually. She got them. And we went to a little church in Mississippi. It was my mother died about a year ago, and they had a memorial service there, so we went to that. And I actually preached for that. Let's see, there's my kids. That's my dad. And that's my aunt and my cousin and my nephew. And then that's my little girl. She just got that dress from her grandmother. All right. All right. Let's see. I sent out something recently, just a little bit ago. Many of you probably haven't gotten it yet. Oop, that's not what I want. The project is due a week from Wednesday. Wednesday is the last class day, and so it's due on that last class day at midnight. So get it to me sometime before midnight. You can just submit it online. A couple of you have already submitted those projects, and they look good so far. I put a rubric up. I actually stole this rubric from my wife. So if you've had her, it's the same rubric that she uses for her projects. But I think it's a good guide for just what to expect for the project. I'll be looking, of course, for things to be grammatically correct. And so that's a small portion, but it's a portion nonetheless. And then I'll also be looking at content. So I'll just leave you to look at this. It sort of help you to shape how you approach this paper, this 1,000-word paper, which is a fairly short paper, but it's not tiny. And then I'll remind you that this is a lot of points. It's what, 150 points, I think? Is that right? 150? So if you haven't done well on an exam or on some of the quizzes, this is a really great place for you to catch some points and sort of catch up in the class. So it should be a place where you can for certain pick up some points. But if you just sort of do a shoddy job, then it's not going to help you really. Okay, but I intend it to be something that helps you. Is that clear? All right, now there is a writing center on campus, so if you have trouble writing, as I know a lot of us do, we can go to the writing center, and they have some nice tutors there. It's free of charge. Actually, you've already paid for it. You pay for it every semester, whether you want to or not. And they take drop-ins, or you can make an appointment and go see too. Or you can come see me, and I can help as well. All right. And then also don't forget there's a reading quiz on Chapter 6 this Thursday, and that'll be at the end of class. Let's go and do the whole chapter for Chapter 6 so we can get prepared for the final coming up pretty soon. Or not the final, but you know that last exam. All right. This will be our 6th quiz, so that means that 2 of those are going to go away. So if you haven't done well on some of the quizzes so far, you need to do really well on this one. Okay? Is that good? All right. I think 6 quizzes is good. And yeah. Yeah. I know that's a lot, but it'll be okay. No, it's not a lot. It's okay. Oh, it's too much. Okay. Well, I think it'll be okay. So, like I said, most of you are doing okay on your quizzes, but if you've had some that are bad, then you want to, you know, buck up on this quiz and really hammer out a good grade. And don't hate me, right? I just bring the news. I don't make it, right? All right. Let's see. And then the last exam is coming up. It's as scheduled during the final time. It'll be just like the other exams, except it's only going to cover one chapter. So um, I think you know what to expect for that. Study the notes, study the book. You'll be good to go. It'll be our fourth exam. It's worth 100 points. It's not a final per se. It's just another exam. All right? Go ahead. It's a regular test. You'll have 2 hours, but it'll be normal length. Actually, yeah, it'll be normal length. It's not really a final, right? But it's during the final time, all right? It counts as a regular exam. And then one last thing is, as part of this course, we have to take a general ed assessment. So at the time of the final, when you're done with the final, you'll take this multiple choice assessment, all right? It will be worth some credit. It'll be extra credit, probably about 5 points. I'll have to see sort of how the class stands. I might make it worth more if I think the class should be standing a little better than they are. But count on 5 points. And those 5 points, you won't get all of them automatically. Whatever percentage you get on that assessment will be what you get for the extra credit. You understand? So if you get 100%, you'll get 5 points. If you get 50%, you'll get 2.5 points, that kind of thing. All right, those will just be the sort of raw points. You can add them to anything that you want, quiz grades, exam grades, whatever. All right, is that exciting? Because you all look really excited right now, like you're bursting with joy. And we'll take that after that fourth exam during the final time. You should have plenty of time. You have 2 hours to take that exam. It usually only takes y'all, 40 minutes, an hour at the most. Okay, any questions, comments? Y'all had a great spring break? Did anybody get married or have a baby? No. I had a student in my other class that did get married, but he didn't show up. But I know that he did get married. All right. Well, we're picking up now with light. Oh, and by the way, I do have your exams from last time, and I'll hand those back at the end of class. All right, this is y'all. Yeah. So please remind me if I forget. I'll try to remember. We're going to be looking at light now. I have some questions that I'll ask as class goes on, but I haven't sent those out yet because I'm not done with them, and I just made them up just like 20 minutes ago. But I'll send these out, and I'll actually put the answers on them as well. Okay? Okay, we're going to deal with sort of what is light. We'll look at geometric optics, refraction, and reflection, mainly refraction. That is the bending of light when it enters different media, in particular when it enters into lenses and different types of media like glass and water. We'll also look at the law of refraction, and then refraction by lenses. We'll look at convex lenses. Convex lens looks like this. This is sort of what we think of when we think of a lens. And then we'll also look at concave lenses, which some of you use for your eyeglasses. And then we'll talk about the eye and how the eye functions as a lens and how it detects light and the different parts of the eye. We'll look at the thin lens equation, the focal length, and then that's it, some various problems that you have with vision. So it's not a terribly long chapter, but there's a lot of cool stuff in it. Y'all cover the eye in your anatomy class, is that right? Okay, so hopefully a lot of the eye stuff you've already seen, and you probably know more than I do about it. All right, so let's first start out with electromagnetic waves. Light is an electromagnetic wave. So light consists of I'm going to call it EM waves for short. That is electromagnetic waves. And in these electromagnetic waves, the electric and magnetic fields oscillate back and forth. We didn't do the previous chapter, so let me just give you sort of a brief primer on what a field is. A field is something that just describes a force, right? So, for example, if I bring two magnets together, they feel a force upon one another. Either they're attracted to one another or they're repelled from one another. And a field describes how strong is that force. So if I'm really close to a magnet, my field is going to be really big. If I'm really far away from a magnet, my field is going to be really small. But in its very essence, a field just describes a force. And you have fields around magnets because they experience these forces or they cause these forces. Right? Y'all played with magnets before. You hold it up next to a piece of magnetic material and it feels a force. Likewise, electric objects, charges, like electrons and protons, they exert forces on one another, and so they also feel fields. Anytime you have something that exerts a force onto something, then you can describe it in terms of a field. So fields are very much related to forces. I'll write that. Fields are proportional to forces in general. And in fact, we define the fields based on the forces. The fields are just something we use to describe the forces. You can also have, we describe the gravitational force in terms of a field. We didn't talk about that when we did gravity, but we can talk about how there's a gravitational field surrounding the Earth, right, that causes this gravitational force. We just use it to describe forces. When we talk about electromagnetic waves, these fields oscillate back and forth. And you can think of the electric field is going to oscillate back and forth with time. And then the magnetic field will also oscillate back and forth with time. If you ever see this on the internet or whatever, these two fields are actually, as they travel through space, they travel perpendicular to one another. So I'm going to try to draw that the best that I can. Yeah, you get the idea, but maybe you don't get the idea. But I have this electric field that moves up and down, and then I have a magnetic field that oscillates back and forth, just like we had with the, waves in the previous section. And they're actually traveling through space perpendicular to one another. Don't worry about that. If you see this elsewhere, you'll see them drawn in that way. But don't sweat that right now. All right. These electromagnetic waves, at their very essence, are caused by moving charges. So EM waves, electromagnetic waves, are caused by moving charges. So light is an electromagnetic wave. Light is also caused by moving charges. Light and EM waves, those are the same thing. A good example of this is a radio transmitter. You know, if you have a radio transmitter, like you have these cell phone towers, like this, and then they have a big pole that sticks up, like this. And I'm talking about these antennae that are on top of radio towers, cell phone towers or whatever. They have electrons on them that travel back and forth. So there's an electron at the bottom of that big metal rod, and they just, by applying an electrical current to it, they can cause this electron to move all the way up the pole, and then it moves all the way back down the pole. So this electron oscillates back and forth at a very regular frequency and at a very regular rate, oscillating back and forth. And what that does is it causes a changing electric field and a changing magnetic field. So when this electron moves back and forth, it causes, like ripples in a pond, this EM wave, changing in the electric field and the magnetic field. So you can think of it as you take like a ball on a string and you bounce it up and down in a water puddle, and it causes these waves. And those waves travel outwards away from the radio transmitter. Right? So as you go about and you see these cell phone towers, that's what those are doing. At its very core, they have this pole, and it moves up and down, electrons move up and down along that pole, that metal pole, and that causes this EM wave, which is transmitted as light. Now, it's not a light that we can see, of course, because it's what type of light that's transmitted by these towers? we'll see this, but this is radio light, right? It's radio radiation, or long wavelength radiation. And we'll see that when we talk about the electromagnetic spectrum. Okay, so moving charges cause light. At their very essence, moving charges cause light. Light has all the same wave properties as we talked about before. So all the same wave properties as those of mechanical waves. That is the longitudinal and transverse waves that we talked about before. They operate all in the same way, and so we can talk about their frequency, and we can talk about their speed, and we can talk about their wavelength. So they have a frequency, they have a speed, they have a wavelength, they have a period. Remember, the frequency is 1 over the period. The velocity is the wavelength times the frequency. And then we can also talk about how they have an amplitude, which we call it A. Right. Don't worry, you're not going to have to know these particular formulae, but just I want you to know that these are just waves. They're very much waves, and they operate in much the same way as the mechanical waves that we dealt with. Right. We'll see a little bit later that not only does light act as a wave, however, that it sometimes acts as a particle as well. And that's sort of been a historical thing that we've seen in science, is how our understanding of light has changed, light being a wave to light being a particle, to now, since Einstein basically, knowing or seeing light as both a wave and a particle. And we'll see that in when we get up into rays. Okay, unlike mechanical waves, electromagnetic waves travel at the same speed. Well, this isn't unlike mechanical waves. Travel at the same speed in a vacuum. This is the speed of light, and we call it c. It has a particular value. It's 3 times 10 to the 8th meters per second. So what is that? 300 million meters per second. So for every second that passes, a light wave travels 300 million meters. This, by the way, just for reference, is 186,000 miles per second. Right, so light travels pretty fast, and in fact, when we talk about we won't talk about fiber optic cables in this chapter, but fiber optic cables operate on this idea that this information travels by light, and it travels very fast, and you can get a lot of data transfer for fiber optic cables, which instead of an electrical signal, you actually have a light signal. All right, now the EM spectrum has a range of radiations. This is the electromagnetic spectrum. And this electromagnetic spectrum ranges from radio waves on one end all the way up to gamma rays on the other end. See, I have a figure. I'll give you just a second and I'll pull it up. The electromagnetic spectrum includes all light. Now there's the light that we can see, but that's just a very small part of the entire electromagnetic spectrum. Y'all are somewhat familiar with this, right, with the EM spectrum? You should have seen it in high school, physical science, or physics, or chemistry even. Right, let me just pull up a little figure. There are a couple of things that I want you to know about this, and I'll send you this figure over on Moodle. Can I minimize this? It'll come back. Oh shoot, I don't have it. Let me just pull it up on the internet. Sorry about that. Oh, which one was the one? I think this might have been it. No, this was it. Sorry, guys. Give me just a second. Okay, there we go. All right, so this shows the electromagnetic spectrum. It ranges from the long wavelength. As I said, I'll send you this on email, but you can do a quick Google search and find this. There are tons of these on the internet. Uh, on the long wavelength end are radio waves. Right, you'll need to know the order of these, and of these that are shown, you'll need to know how these fall in the order. So radio wavelengths are very long wavelengths, meters to kilometers long. So use these for radio communications. And then you move into microwaves. Your cellular phones are on the order of microwaves, about the same wavelength as microwaves. From radio to microwaves, the infrared spectrum, which we had talked about before, remember the two British guys with the refrigerator? They had an infrared camera and they were measuring infrared radiation. So infrared light is just to the low energy side of visible light. So we have this little spectrum here of visible light, and this little sliver of the electromagnetic spectrum is what we can see. And then, of course, within the visible spectrum, y'all know the mnemonic, right, for the order of the visible spectrum? Roy something or another. Okay, within visible light, you have Roy G. Biv. And we're going here from low energy to high energy. And within the visible spectrum, it goes red, orange, yellow, green, blue, indigo, and violet, with red being the lower energy of the light and violet being the higher energy of the light. Right? So if you look at stars, for example, if you have a blue star and you have a red star, which one of those is going to be hotter, you think? A blue star or a red star? The blue star is hotter because blue light is higher energy, and it's hotter, or rather it puts out blue light because it's a hotter star than the red star. All right, so Roy G. Biv. And then just to the high energy side of visible, we have the ultraviolet, and that's actually what damages your skin when you go out in the sun. And then on the higher energy side, we have X-rays, which we use for imaging, of course, and then gamma rays, which you can use for treatment of various, well, for radiation for cancer and what have you. But gamma rays can be very damaging to the body because they have such a high energy. They can actually cause cells to be destroyed, which is why it's used for cancer treatment. All right, so this is the electromagnetic spectrum. So I'll send this out to you, this diagram, or you can Google it yourself, but I'll put it on Moodle for y'all. You'll need to know that this is from low energy to high energy. You also need to know that this runs from long wavelength to short wavelength. So radio waves have a very long wavelength, and gamma rays have a very short wavelength. And then implied in that, then, that it runs from low frequency to high frequency. Because you remember, frequency and wavelength are inversely related. So if I have a radio wave with a very long wavelength, that means it has a very small frequency. All right. Can I take this away now? I'll send this out to y'all. All right, so that's the electromagnetic spectrum. As I said, visible light is just a small sliver in this. It runs, I've already written this, but let me write it again. It runs from low energy to high energy, Roy G. Biv, where red is the lower energy of those colors, and then purple or violet is the higher energy, just before you get to ultraviolet. Visible light is not caused by an electron on a metal rod moving up and down, but it is caused by moving charges. Visible light is caused by electrons moving in or out of energy states. All right, so if you have a nucleus with our positive charge, and then we have these orbitals. This is a model of an atom. If I have an electron that moves from one orbital to the next orbital, it'll emit a photon, it'll emit light, and that's how light is caused. The visible light that we see is always caused by electrons moving from one energy level of an atom to another energy level of an atom. You've seen energy levels of atoms before? That's probably 8th grade, maybe chemistry, college chemistry. All right, so visible light is caused by these electrons moving in and out of energy states. The light from these fluorescent bulbs, that's what causes that. Electrons moving in and out of energy states. Likewise for incandescent bulbs, you have that occurring as well. So visible light is caused by moving charges, but it's different from moving charges that cause radio waves. Visible light is caused by these charges moving in and within the states of an atom. All right. The energy range then, I didn't write this. Let me write it just a second here. We can calculate the energy of an electromagnetic wave is equal to H times F. Not terribly important what H is. It's just a constant. It's called Planck's constant. And you're not going to have to calculate the energy of a photon or of a light wave. But I want you to know that the energy is proportional to the frequency. All right, so if I have a higher frequency, that means that it's going to have more energy. So the energy is proportional to the frequency. And we use units for energy that are a little bit different. You might have seen this before, but we use units for energy not for joules, but the units that we use for energy for light is called the electron volt. If you take an electron and you apply a 1-volt battery to it that causes that electron to move, it will have 1 electron volt of energy. It speeds it up and it gains that much energy. So we use this electron volt, which is also called the EV, to describe the energy of light, these electromagnetic waves. And then the energy range for visible light is on the order of just a few electron volts. Is about 1.8 eV to 3.1 eV. All right. You don't have to know those particular numbers, but just know that it's just a couple of eV. It's just a couple of electron volts on the order of that. And that's an important number because that's roughly the energy between these energy states. So this 1.8 to 3.1 eV, if you're looking at most atoms, that's going to be the energy between those energy states. All right, so when I have an electron that moves from one energy state to another, it emits light that is at the same energy as the difference between these two energy states. You with me on this? Yeah? All right. I'm not going to ask for calculations on this, but I do want you to have sort of a basic understanding of where this light comes from. And these energies, as I said, are the same as the differences between these two energy states. So electrons, as they move further away or closer to the nucleus of an atom, it changes the energy of that electron. All right, let's look at waves and rays. The author here, he sort of does a funny thing where he talks about the particle-like nature of light and the wave-like nature of light. He talks about waves, first of all, wave fronts. If you think about a source of light, like this lamp, for example, but just a point source of light, It's going to emit light all around it. It's called isotropic. It's pointing in all directions. So light is going to come out away from this light bulb in all directions. And you can think of it as going out as these wave fronts. So as light comes away from this light bulb, it travels outward, and you can draw it as wave fronts, right? You could draw an infinite number of wave fronts, right, to represent the waves that travel outward away from this point source of light. And so we would call these wave fronts. And they're just there to represent the wave. I'll show you why this is relevant a little bit later. When we look at refraction, it'll be helpful to think about light as a wave front, right? So you can think about this light as it travels out as a front of waves, the light traveling out as this front of waves. Now, you can also think about it in terms of rays. So if instead of drawing these wave fronts, I draw rays that emanate outward from this light source, I would call these rays. And they're very similar to the wave fronts. They just show the direction that the light is traveling. So we can talk about wave fronts, and then we can also talk about rays. When we see refraction in a bit, it'll be useful to think of light as these wave fronts. And if it doesn't make sense to you now, just hold on. I think it'll make sense in just a bit. When we talk about geometrical optics, that is lenses and mirrors and the like, it'll be useful to think of them as rays. Right, so if that doesn't make sense to you now, don't sweat it. We'll come back to it in just a bit. All right, so let's look at geometrical optics. Actually, let me see if I have any questions. Yeah, I have a few questions. Let's go ahead and do these questions. Oh, I haven't opened it yet. As I said, I will send these out this afternoon. I need to finish them up. And then later I'll send out all the answers to them as well. I don't know if you noticed, but the last test had some of the questions that I had asked in class. It's always been that way, but y'all did notice that there were some of the questions from the test from in class? Okay, so it's a good way to study. You'll probably see some of these. All right, so let's see. Light can be described as which of these? A magnetic wave, an electric wave, a longitudinal wave, both A and B, or both A, B, and C. Do y'all remember what a longitudinal wave is, by the way? It was also called a compressional wave. It's a sound wave, right? Magnetic, electric, longitudinal, A and B, or A, B, and C. All right, I'll stop at, say, 55, 55. Okay, D is right. Very good. You can think of it as it is an electromagnetic wave. That is a wave, an oscillating of the electric field and an oscillation of the magnetic field. We call it an electromagnetic wave. It is not a longitudinal wave, however. A longitudinal wave is different. Remember, it compressed the medium, and we're not doing that here with a light wave. It's a transverse wave, in fact. What causes an electromagnetic wave? Moving charges, light energy, mechanical energy, alternating medium, or virtual motion. All right, 35, I'll stop. 35. A is right. So light or electromagnetic waves are caused by moving charges. They can be different kinds of moving charges, but they're always caused by moving charges. A is the right answer. What is the proper order of these types of radiation in order from highest to lowest energy? So I have gamma, radio, visible, and infrared. Place them in order from highest energy to lowest energy. From highest to lowest energy. All right, just a few more seconds. I'll stop at 1:10. As I said, I'll post these on Moodle. Let's see, most of you put C. Gamma, visible, infrared, and radio. That's right. Gamma radiation, remember, is the highest energy. That's why it's damaging to your body. Visible is next. And then infrared is lower energy than visible. It doesn't hurt you if it touches you, like ultraviolet would. And then radio is the lowest energy of all. And so C is the right answer. So I think one more. The energy of an electromagnetic wave is directly proportional to what of that wave? The amplitude, frequency, period, or the duration of the wave? The energy of an EM wave is proportional to what? It's directly proportional. All right, so that means if it goes up, the energy goes up. All right, just a few more seconds. Let's see. I'll stop at 40. B is right. Very good. And then one more. Visible light is caused by which of these? I'll stop at 30. I'll stop at 40 seconds. Very good. So visible light, all visible light is caused by these electrons moving back and forth. And when they move between energy states, they emit what we call a photon, a little packet of light. And that's what you see, the energy from that electron moving back and forth. Right, we'll come back to this. All right, so now let's look at geometric optics. When we say geometrical optics, we generally refer to that as how do we trace light through different optical elements, lenses and mirrors, for example. But before we get to lenses, which is what we'll deal with first, we want to define something called refraction. And refraction is purely a wave phenomena. It only happens for waves, but since light is a wave, it occurs for waves. And the waves travel at different speeds in a different medium. You see this in water waves, which are a type of transverse wave, out on the lake. If you'll notice, you'll see the waves out on the lake, but then when they enter a different part of the lake, maybe where it's not as deep or where the temperature has changed, that medium changes, and you'll see the waves will travel slightly differently. They'll maybe get a greater frequency or a lesser frequency. Take a look next time you go out, like on the water. You can see this, especially when it moves to shallower water. Those waves will actually change. And the reason is because the waves are traveling at different speeds. So we see it very clearly in, we saw this also with sound waves as well. When they enter into different media, they travel at different speeds. We see it with light waves, and it causes refraction. Now we define this based on the index of refraction. Which is a quantity that we call n. And n is defined as the speed of light divided by the velocity of light in that medium. So this is that speed of light in a vacuum. That's 3 times 10 to the 8th meters per second. And this is the speed of light in a medium. When light enters a medium, it slows down. When light enters a medium, it slows down. When light enters a medium, it slows down. That means that our index of refraction here is always going to be greater than 1. So because of this, because light slows down when it enters a medium, n is always bigger than 1, or is always bigger than 1. So n is always bigger than 1. All right, for a vacuum, if your light is traveling in a vacuum, the index of refraction will equal 1, right? Because C and V would be the same. But anytime it enters a medium, this value is going to be smaller than this value, and so it will slow down. So for example, if our index of refraction is, say, 1.5, which is what it is roughly for glass. Most glass has an index of refraction of about 1.5. Then the velocity of the light wave in that glass is equal to c divided by n. I just took that equation, I switched around and solved it for v, which is going to be 3 times 10 to the 8th meters per second, divided by 1.5, which 1.5 cancels there and leaves me with a 2. It's going to be 2 times 10 to the 8th meters per second. All right, so this index of refraction just describes how the speed of light causes, or how the speed of light is affected in different media. This, by the way, is a really great way to determine unknown materials or unknown substances. So you can measure n to determine unknown substances. Scientists and engineers do this a lot with gases. If you have a gas and you don't know what kind of gas it is, you can run a laser through it, and you can measure the speed of light of that laser as it travels through that unknown gas, and then you get the index of refraction. Since we know these indices of refraction really well, it becomes a really nice way to determine unknown substances. So if you ever have a gas and you're just not really sure what it is, just run a laser through it, measure the speed of light as it travels through there, and there you go. You got your gas, whatever it is. All right? All right, good. So that's a very useful thing to find out unknown gases. Now, traveling at different speeds in a media can cause the light to bend. Traveling at different speeds or to a medium can cause light to bend. And this is how optics work, because they can take light that's traveling in a straight line and move it so that it travels in a different path. Now, if I have, say I'm moving from air to glass. Now, air, we typically say, has an index of refraction equal to 1. It's actually not exactly equal to 1 because it's a gas. It's actually like 1.000 something, but we'll just assume that it's 1. It's a vacuum if you want to say that. And then glass has an index of refraction equal to 1.5. If I have a light ray that travels straight on to the glass interface, here I have a speed of 3 times 10 to the 8th meters per second. And when it travels here, it still travels in a straight line. It's just going to travel a little bit more slowly. So it's going to travel at 2 times 10 to the 8th meters per second, just like we found before. So as it's traveling through the air into the glass, it slows down when it enters that glass. However, if I come at it at an angle like this, it's going to bend one way or another. Now this line is what we'll measure that angle from. This line is called the normal line. I don't know why we call it normal. Normal is just another word for what? Do y'all know? In mathematical terms, it's perpendicular, right? So I don't know why I just don't call it perpendicular. We have like 4 different words that all mean perpendicular, and they all mean perpendicular. So normal just means that this angle is 90 degrees. But we measure the angle of this light ray from the normal line. So we'll see that sort of pop up in questions. I just want you to know what that means. The normal line is just something that's perpendicular to the surface. So I can measure this angle. This will be my, I'll call it theta 1, that angle. And now I want to think about, and you'll have some questions like this on the next exam, what direction is it going to bend? You can think about it in a number of different ways. Y'all ever had like a twin propeller boat? A boat that has twin propellers on it? Or a bulldozer? You ever driven a bulldozer? Every day, okay. Well, on a bulldozer, on a twin propeller boat, you have 2 things that go at different speeds, right? If you want to go right on a bulldozer, you make this side go faster, and then it turns you in this direction, and this side goes slower. The same idea is for a twin propeller boat, right? You can make one side go faster, and it'll cause your boat to turn. And so you can think about this. Typically, though, in physics classes, they always talk about the marching band analogy, but it's a similar idea. Imagine that I have a marching band that's marching along. What did I play in the marching band? Does anybody know? I've told y'all this before. Tuba, thank you, very good. Or the sousaphone, right, in the marching band. So the marching band marches along, and you can think of it as they're marching here on asphalt. Because on asphalt, you're going to go the fastest, right? It's a very easy medium to travel through. And here you can think about the glass as like a muddy field. Right? And in a muddy field, is the marching band going to go faster or slower? Slower, right? So this is the same idea. And the marching band is nice because it helps you think about the wave fronts. Remember those wave fronts that we were talking about? You can imagine these wave fronts that are traveling along where I've drawn this ray. And so I have this whole front of waves that is traveling towards this air glass interface. Or I have this marching band that's traveling towards this asphalt muddy field interface. The same ideas will apply. Now, when this marching band gets up to this point, the people that are right here, as they enter this muddy field, are going to slow down. But the people that are over here are going to be going faster. So when this marching band, or when this light ray, or this front of waves moves from the air to the glass, or the asphalt to the muddy field, are they going to move in a direction that is either straight, meaning they don't bend at all, or are they going to bend away from the normal, or are they going to bend towards the normal? They're going to bend towards the normal. Let me show you. So if these guys on this upper part, if they speed, these guys up here are going faster while these guys have slowed down, that means this whole thing is going to turn around like that. And then, once it enters this new medium fully, let me redraw that to exaggerate it. Once they enter this new medium, they'll be like this. And then I can draw these wave fronts. like that. So these are wave fronts. Remember, that's what we talked about before. Actually, this is a combination of rays, the red line, and wave fronts, the black lines. And both of them are useful to help you understand refraction. The ray will just help you, well, where does the light go? But the wave fronts will help you to conceptualize or imagine what the medium is causing the light to do and what direction does it cause it to bend. Now, if it was moving from the muddy field to the asphalt, would it bend towards the normal or away from the normal? Away from the normal. So if I'm traveling instead up in this direction, the same thing will apply, except it's going to bend now this direction. In fact, light is always that way. It's always reversible. If it does one thing in one direction, it's always going to do the opposite thing in the other direction. All right, we'll see this a little bit later. I'll ask you another question about this in a bit. I have a little video. This is a student did this. This has lots of applications, by the way, like lenses. That's the idea behind lenses, because light traveling through the lenses will bend one direction or the other. It's also the concept behind fiber optic cables, because the fiber optic cables will cause the light to bend in upon itself, and so the light will never leave the fiber optic cables. A lot of different applications that are very important. Let me show you a little video. All right, so that's a type of refraction. This bending of light just because of a difference in speed. It's traveling at a different speed that causes it to bend. Let's look at the law of refraction. I'm just going to throw this up here. You're not going to have to calculate anything with this. But I want to show you a couple of things about it. Actually, I don't even know that I need to write this. No, let's not even muddy that up. All right, so let's imagine that we have a slab of glass. All right, so if I have a slab of glass, I'm going to get a light ray that will travel through this. So if I have a light ray here, it travels through. I have my normal line there. Will this light ray bend towards or away from the normal as it moves from air to glass? Towards or away? It's going to move towards the normal, right? So my light ray will bend in this direction. And then over here, because now it's moving from glass to air, it's going to bend away from the normal. And so my light ray will look like this. And so what I've done here is you've taken this light ray and you've shifted it off to the side. So here, the light ray is moving in this direction. And if there wasn't any glass there, it would just keep moving straight on. Right? But what you've done is you've caused it to shift from one side to another. You can see this pretty simply. I brought a little slab of glass here. And a laser. So this is just a green laser. Let's do it right here. So if I shine, can y'all see that in the back? See the laser on the board? Oh, I'm sorry, you're getting a little reflection. Y'all see that on the board? All right, so if I move it up and down like this, it doesn't change where the laser goes on the board, right? It moves up and down, but it doesn't change where on the board it's lying. But if I have it go at an angle through the board, watch the point on the board. If I move it up, it's going to shift over. See how it shifts over? It shifts over about 5 or 6 inches maybe. You'll see that? That's the same thing that's happening here. The light ray comes in. If it went straight, it would come straight down there. But the bending of the light causes it to bend off to the side, and then that causes it to move over. Actually getting a little diffraction is there as well. All right, so that's a type of refraction through a slab of glass. You can also see refraction through a prism. I didn't bring a prism, but it works very similarly. You might have seen prisms before. They're used for a number of different purposes. But if I have a triangular prism like this, I can have a ray of light that will come in. It will bend towards the normal, like that, and then it will bend away from the normal. And prisms have a lot of different uses for dealing with light, which we're not going to get into here. But anyway, these different media can cause the light to bend just because light travels at different rates within the medium. Okay, so the whole point of this is that the bending of light occurs when it enters into the eye. Because your eye has a series of lenses, really just one lens that's made up of several different parts, that causes the light to bend and focuses it onto your retina where it's detected and signals sent to the brain. So we want to look at refraction by a lens. Mainly we're going to look at convex lenses, but we'll also throw in some concave lenses as well because they're useful for correcting, not reflection, refracting. Right, the cornea is a type of lens. The cornea is a curved surface. We'll get into the different parts of the eye probably next time. But the cornea is a curved surface. It's a type of lens. And then within the eye, you also have another part of the eye actually called the lens that is also a curved surface and causes the light to bend. But the cornea is the primary way that you bend light going into your eye. And we will have two different types of lenses that we'll talk about. So since this cornea is a type of lens, we'll want to discuss these two different types of lenses. One is called a convex lens. Both of these, by the way, we call spherical lenses. And we call them spherical lenses because you can imagine that they're cut out of spherical surfaces. Now, in the convex lens, imagine that you have two circles. There's one circle, and then I have another circle, and they overlap slightly. The convex lens would be like this center part. If I could just take out that little part, that would be my convex lens. I can describe a couple of different things about this. I can describe the center of curvature for this side and the center of curvature for this side. So this would be the radius here, and this is also the radius. So my convex lens, I'll draw it like this. It's just a surface, a curved surface. They're spherical on both sides, so both of these sides have a spherical surface. And then I also have radii, which correspond to the center of curvature. So this is called the center of curvature. All right? That's a convex lens. This is also known as a converging lens for reasons I'll talk about in just a bit. This is the type of lens in your eye. It's a convex lens. So this is also in your eye. There's a second type of lens called a concave lens, which is important because you can use the concave lens to correct for certain problems with eyesight. A concave lens, I think it's called this because it sort of caves in. Concave lens, if you imagine that you have two spheres, or two spheres that are like this, the concave lens would be the lens that is outlined here. Right, so this would be, the blue portion would be the concave lens. So in a similar way with the convex lens, this has two radii, or two centers of curvature on either side. So the concave lens sort of looks like a nuclear cooling tower. It has a center of curvature over here and a center of curvature over here. Remember, the center of curvature is just the radius of that sphere from which it's been cut. So that's a convex lens, and that's a concave lens. The concave lens is also called a diverging lens. Both of these are used in glasses depending upon the problem that you have, whether you're near or farsighted. And they're also used for other purposes. So like, for example, a convex lens, the ones on the top, are used for magnifying glasses. And I'll pass around a convex lens in just a bit. There are a number of other different types of lenses, if I included them here. Yeah. Concave is what? Right, they're both spherical mirrors. When I say spherical, that just means that they are cut out of a sphere. So I start with these spherical surfaces. The only difference between the convex and the concave is sort of, are these two spherical surfaces squished together, or are they pulled apart? Sort of what is the orientation of those spherical surfaces? And for the concave, it's like they're pulled apart, and you're taking this center portion. All right. There are other types of lenses as well. Pull them up. You just need to know these in name. This is a convex lens right here, and we'll be dealing with it. And this is a concave lens. They call it biconvex here. That means that it's convex on both sides. But you can also have different ones that are, say, convex on one side, like this one. And then it's a plano-convex lens here, meaning that it's flat. So this is like a plane lens on this side. And then for the biconcave, this is like the one that we just shown, where it's concave on both sides. And then you can also have a plano-concave, where it's planar on one side and concave on the other. Then you can also have meniscus, convex, and concave. These are different. Don't worry about these. I just want you to know the other four. But in case you ever see these again, the meniscus lenses are different in the, one of them is wider out on the edge, and one of them is really skinny out on the edge. And these have different purposes that we're not going to get into. All right, but I do want you to know these four types of lenses and just be able to identify them if I were to give them to you. It's pretty simple. If you know concave and convex, if they're planar on one side, it's going to be plano, whatever, concave or convex. I'll give all of these to you. I'll send you this diagram on Moodle. Okay? So those are the types of lenses, and you can sort of switch them up like that. I come away from this? A few more minutes. Let's see, do I have some more questions? I think I might. Yeah, let's do a few questions. Okay, so as light moves from air to water, what happens to its speed? Does its speed increase, decrease, remain the same, or does it depend upon the amount of water? As light moves from air to water, what happens to the light's speed? Increase, decrease, the same, or does it depend on the amount of water? I'll stop at 40 seconds. All right, B is good. That's right. Very good. When it moves from air, which we sort of think of as a vacuum, it's basically the same speed. And then it moves to another medium like water, the speed is going to decrease. Light and air is incident on a slab of glass. Which of these describe the path of the refracted ray? So let me draw this for you. This is my glass. This is air. My light ray comes in like this. What's going to happen to that light ray? Will it bend? Will it not bend at all? Bend towards the normal or bend away from the normal? Just a few more seconds. I'll stop it. Let's say 45. Okay, B is right. You can draw your wave fronts to help you think about this. So I draw some wave fronts. Here I know that these marching band folks are going to slow down, and these guys are going to keep going fast, so they're going to sort of bend in this direction, and that's going to cause it to bend towards the normal. So B is the right answer. That means that this angle is smaller than this angle. All right, light moves through a slab of glass. This is the incident light ray right here. What is the path that it would take? Right. Would it bend up and take path A? Would it keep going straight and take path B? Or would it bend down and take path C? What's the path that this light ray would take, moving from air to glass? All right, I'll stop at 55, 55. Okay, we're sort of all over the board here. B is not the right answer, right? Because it's going to be bent by this slab of glass, just like I did with this slab of acrylic, actually, but it's light glass. Actually, A is the right answer here. Let me show you, if you encounter a problem like this, let me show you how you can think about this. You can do it like we've been doing, where, I imagine this marching band or this wave of fronts. This is going to slow down. This guy's going to speed up. That means that it's going to bend towards the normal. And so it'll bend up there. And then if I imagine the wave front's inside the glass, as it comes along this side, it's going to speed up when it enters the air. And so it's going to bend around that way. And it will travel like that. All right. It's shifted from one side to another, but it's still traveling in the same direction. I'm just shifting it up to travel like that. So A is the right answer. I think I have one more question, or a couple more questions, and I'll hand out your exams. Which of these best describes the index of refraction? Greater than 1, greater than 0, less than 1, or in between 1 and negative 1? And then I have one other question after this. It's super easy though. All right. I'll stop at 30 seconds. Or 5 more seconds. Okay, very good. Index is always greater than 1. Right, for a vacuum, it's equal to 1, but for all other media, it's always greater than 1. So A is the right answer. And when light enters a medium, it does what? It speeds up. That means like it goes from vacuum to a medium. What does it do? Speed up, slow down, or keep the same speed? And I'm going to hand back your exams here in just a second. I'll stop at 25 seconds. 25 seconds. Okay, very good. B is the right answer. Moving from a vacuum into a medium like glass, it's always going to slow down. We only have 2 more class days, but that should be plenty of time to finish this. We will have a couple of presentations on that last class day, but that will only take about 10 or 15 minutes. And then we'll be set up for the exam come up in May. I don't know when. Do y'all know the date of the exam, the final? May 12th, yeah. It's in the, okay, it's in the syllabus, and it's on the university schedule, too. So if you can ask me if you forget. All right, I'm going to hand